In this lesson, we're going to use the law of reflection to figure out how we can see images in plane mirrors and where those images appear. We're also going to learn that those are virtual images, and virtual is different than real. So what I have over here is a mirror. This is my mirror on an edge-on view. So the person is looking into the mirror this way. That's an eyeball over here. And there's an object, that's this thing, it's a physical thing, and light is coming off of that in all directions. Now, some of those light rays hit the mirror and are reflected into the eye. And a mirror does what's called specular reflection or mirror reflection. It always follows the law of reflection, right? And it's a nice smooth surface. So incoming rays, if I had, like here's a mirror, and if I had a bundle of incoming rays that came this way, they would all bounce out parallel to each other if they all came in parallel to each other, which means I can only see these light rays if my eyeball's up here. Now, if I have a rough surface and I get diffuse reflection, then I have a much wider viewing angle. But diffuse reflection comes from a rough surface, and when I say rough, I don't mean necessarily like bumpy that you can feel it. It can be microscopically rough. To get a nice regular reflection from a mirror, you need a very, very smooth surface. So good mirrors are made by making a very smooth, flat piece of glass and then putting a nice shiny layer of metal on the back, usually silver. All right, so we've got this plane mirror, and what I have drawn over here is this object, which is an arrow pointing up. I've got my eye, and so what I have is light from the bottom of this object. I've got a bundle of light rays that comes up, hits the mirror, and follows the angle or the law of reflection. So the angle of incidence is equal to the angle of reflection. So I'm going to concentrate on this lower ray here, this one. And so this angle is equal to that angle. So the angle of incidence is equal to the angle of reflection. That's the law of reflection. And that same thing holds true for this other light ray, but I'm going to trace back where those light rays appear to come from. So our eye doesn't understand that the light's bouncing off of the mirror. Instead, what our eye assumes is light travels in straight lines. So if I trace this point back, and I trace this point back, those 2 points appear to come from the same point, and it's the point that corresponds to that point on my arrow. So there's the base of my arrow. I've done the same thing with light rays that are coming from the top of the arrow. And again, I've got this ray that appears to come from somewhere back here, and this ray that also comes from back there. And so those 2 points focus on up here, so that's the tip of my arrow, and so I can fill in the rest. And so what I get, that's a bad drawing, but is this arrow, this image that appears to be behind the mirror. Now I say appears to be because these light rays that I have drawn dashed, those don't actually exist back there. There is no light passing back behind the mirror. And that's what I mean when I say a virtual image. So a virtual image means no light passes through where the image appears to be. Okay? Now, this is to distinguish it from a real image. And we'll look at real images when we looked at curved mirrors, but a real image, there actually is light passing through where the image appears to be, and that means you can actually project the image. So a virtual image cannot be projected. It only exists in the eye. So your eye interprets these light rays as coming from these points, even though they actually came from here, because our eye says, oh, well, these are light rays, so they travel in straight lines. So I get this image that forms on the other side of the mirror, but it doesn't exist anywhere but in our eye. But we do have the idea of image distance. How far behind the mirror does that image form? And to do this, we're going to use some geometry, and I'm going to draw a slightly bigger diagram. So let's make it a little less convoluted. There's my floor, here's my mirror, and I'm only going to put one light ray on here, if I can. So here's my object, here's my image. And the distance from the mirror to the object is called the object distance, or DO. The distance from my image to my mirror is called the image distance, or DI. Now, what I have is light that leaves the bottom and bounces off into my eye, and it follows this law of reflection. And this light appears to come from back there, right? So this is a straight line. This is a 90-degree angle, this is a 90-degree angle. Now we know that this angle right here is the reflected ray, and this angle right here, the incident ray. Those two angles are the same. So angle of incidence is equal to the angle of reflection. So now we're going to use some geometry to show that these triangles are actually congruent, and so that the image distance is equal to the object distance. So this is the normal right here, and the normal is perpendicular to the mirror, and the mirror is perpendicular to the floor. So this is also a right angle. Now, this angle right here, theta I, the incident angle, by law of reflection is equal to theta r, the angle of reflection. But this angle right here is also equal to that angle right there because those are vertical angles. And that makes this angle congruent to that angle because those are alternate interior angles of transversal cutting two parallel lines. Now, same thing holds over here. This angle is equal to this angle, which means I have all three angles, so this angle and this angle are the same, which makes this angle and this angle the same. So I have three angles congruent, which does not prove congruent triangles, but this side is common to both of them, so it's congruent to itself. So what I have is angle side angle and a right triangle, which tells me that these two triangles are in fact congruent. So the object distance is equal to the image distance. So the image in the mirror appears as far behind the mirror as the object is in front of the mirror.